and then we will get started. Okay, all right, exams on Wednesday. This is the big review session. The goal, as usual, is just to kind of go through the content. It's a 1 hour to cover a lot of content, so I won't be able to reteach all the content. The goal is to kind of go through the big topics and really kind of show you where you're strong, show you where you're weak. All right, so we'll do a review, have you do some questions, and answer some questions, hopefully. All right, so we will get started with section 2.8 and 2.9. We started this portion of the course talking about vector spaces, which is a big collection of stuff. And if those elements satisfy these 10 big properties, we dubbed that set of stuff a vector space. And there was a whole bunch of special analysis we could then do to our vector space. So it was a collection of objects where we defined addition and scalar multiplication, satisfy the big 10 properties. Okay? So if I have a set of stuff, so it's kind of a pain in the butt to show it's a vector space. Luckily, if we have a smaller set that's inside of a vector space, we actually didn't have to show all this stuff. Okay? So really our focus on subspaces. If we have a small set of stuff inside of a vector space, we only need to show 3 things are true to show that subset is a subspace. We need to show that 0 was in the set. We need to show the set was closed under vector addition and scalar multiplication. Okay? So our focus was on identifying subspaces of larger vector spaces. Okay, so let's see if we can do that with our 3 big things to test. I got 3 sets to find here, and this is our first learning catalytics question. So I'll consider the set of all second-degree polynomials, where we talk about scalar multiplication and addition, same as we always add polynomials. Set of all 2 by 2 matrices, and the set of all lists of 3 numbers. One of those sets is not a subspace. The other 2 are. Which of the following is not a vector space? All right, 10 students in learning catalytics, 9 responses so far, 44% correct. And the correct answer here is A. A is not a vector space. Well, why not? Well, let's consider a vector in the space. So if I let V be some vector in a space, that's any second-degree polynomial. So for instance, if I thought of that guy, that's one element of this potential space, one set here, one vector if it were a vector space. If we grab another element from this space, call it x squared minus 3x plus 4. Okay. Now what happens if I add these 2 elements? Well, if I add them together, I get 0x squared minus x plus 7. I've taken a second-degree polynomial, added it to a second-degree polynomial, and the result, not a second-degree polynomial. Okay. So I've added my way out of this set, which means this set of stuff is not a vector space. So it's a subset, not a subspace. Okay. So that's one example of a set not being closed under addition. Any questions about that example? Okay, so then we have a reminder of what those big 3 properties were. So a subset of vectors form a vector space. I don't know what that sentence says there. Basically, we have a set of items within a vector space. They form a subspace if we satisfy our 3 conditions here, if they're closed under vector addition, closed under scalar multiplication, and they contain the 0 vector. Okay, so those are the ones we need to show that a subset is a subspace. All right, so now let's look at this example. Consider all the possible solutions to the equation ax equals b for some matrix. Okay, so as an example, I got a matrix equation here where I have ax equals some b vector specifically. If I think of all the solutions to any general ax equals b, if I look at just the possible solutions, do the solutions form a vector space, a subspace? That's our next learning catalytics question. So I'll send that guy to you real quick. So I think of all the solutions to ax equals b. Does that form a subspace? All right, 9 responses so far, 10 responses. All right, well, let's think of our 3 big criteria, right? 1, is 0 in the subset? 2, is it closed under vector addition and scalar multiplication? Well, let's check 0. If I were to plug in 0, in other words, if I looked at this guy and I multiplied it by 0, would I get to 2, 1, 0, 0? No, I would not. So 0 is not a solution to this equation. If 0 is not in the subset, it can't be a subspace. Okay? Another way we can think about it is, let's pretend that x1 was a solution. Well, that means if I took that x1 and I multiplied it by a, I would get 2, 1, 0, 0. Right? That's what it would mean for it to be a solution. Let's say that x2 is a solution. Well, then if I multiply that by a, I would get 2, 1, 0, 0. It would be a solution, right? But then if I added 2 solutions together, is that guy going to be a solution? Well, if I multiply by a, will I get to 2, 1, 0, 0? Well, if I distribute that a, I would get this. But this guy is 2, 1, 0, 0, and that guy is 2, 1, 0, 0. So that means altogether it's 4, 2, 0, 0, which means this thing is not a solution. It's not a value I multiply by a to get to 2, 1, 0, 0. So that means this would not be closed under vector addition. So in general, the set of all solutions to ax equals b is not a vector space. However, the solutions to ax equals 0, that's special. Okay? That is a vector space. Is 0 a solution to ax equals 0? Yeah, if we plug in x equals 0, we'll always get a true statement there. Okay? Then, is it closed under vector addition? Well, if x1 is a solution, what does that mean? That means a times x1 is equal to 0. If x2 is a solution, that means that a times x2 is equal to 0. If I added x1, some random solution, to another random solution, would that be a solution? Well, I kind of follow the same flow I did before. I'll distribute to get to this, but a times x1 is equal to 0, right? A whole bunch of zeros there. And a times x2 is equal to 0. And if I add them together, I get 0. So that means if I take any 2 solutions, I add them together, I get another solution. I can do the same thing with scalar multiplication. So ax equals 0 is a subspace, a vector space. And it's actually kind of one of our favorite spaces. We have a special name for that guy. What is the name for that special space? Not everybody all at once.
Null space?
Null space, all right, the null space. The null space is the set of all solutions to ax equals 0, all right. All right, so those are the 2 special spaces we're going to focus on. The null space, set of all solutions, the homogeneous equation, ax equals 0. And the column space, set of all linear combinations of the columns of A. Okay. All right, null space, set of all solutions to the homogeneous equation ax equals 0. In other words, it is the x's that get mapped to 0. Okay. Now, we got to know the definition, solutions to x equals 0, because that tells us how to find them. All we do is solve the homogeneous matrix equation. Augment with 0, row reduce, find our solutions. Okay, that's how we find the null space. But think about it is the x's that map to 0 tells me that it's some subset of the x's. Okay, so if I look at a matrix that's say 4 by 3 maybe, okay, that's my A, I'm going to multiply it by an x. Just for me to be able to do the multiplication, how big does x have to be? We'll say 3 by 1 because we'll look at it as a vector, right? But that first value's got to be 3, right? Just so I can do the multiplication, which means x, this x value, right? It lives in R3. That's where that guy lives. So if the null space is a subset of the x's, the null space must be a subspace that lives in R3. Okay, so I can tell that right from the dimensions of the matrix A, that the null space of A is a subset of R3. Now the column space, it's a set of all linear combinations of the columns of A. All right. Well, what does that guy mean? A set of linear combinations. Well, if I took A times X and I did this multiplication, it is generating linear combinations. Right? When we take a matrix and multiply by a vector, one way we can do that multiplication is the linear combination method. Okay? So that means the linear combinations are exactly the B's that you get. Okay? So what's the column space? It is all the possible B's. Okay? It's the span of the columns. It's the range of the transformation. It's all the possible outputs you get. Okay? So if I took my 4×3 matrix A and I multiply by my 3×1 vector X, the result, B over here, how big would that one have to be? 4×1, absolutely, 4×1. That means if the B's, all the possible B's are the column space, that means the column space of A must be a subspace of R4. Okay? So I can tell that just by knowing that the null space is a subset of the x's. The x is the map to 0, and the column space is all the possible B's. Okay? So let's stretch that one notch higher here. Think about a 3×6 matrix for your next learning catalytics question. I will deliver that one to you. And that one looks like this. All right, consider that matrix a 3×6. The column space of this matrix is a subspace of R what? Column space, subspace of what larger vector space? The column space is a subspace of what larger space? Is the column space related to the x's or to the b's? Think of that definition of the column space. It's the linear combinations of the columns. If you take a linear combination of these columns, what kind of result do you get? All right, 12 students in learning catalytics so far, 9 responses. All right, about 40% correct here. So this is a 3×6, so the x would have to be a 6×1, and the b would have to be a 3×1. If I take linear combinations of these columns, each of the columns lives in R3. If I add a bunch of them together, I get a vector in R3. So this is going to be A, it's going to be in R3. Okay. Now what about the null space? Well, the null space is just the x's that map to 0, right? The x to multiply this m by would have to be a 6×1 vector. So the null space would be a subset of R6, whereas the column space is a subset of R3. Any questions? Any questions about this so far? Remember, it's going to be your score on the exam, so get your questions answered in the review session. Any questions from the online group? All right, I'll try to keep up with a little of the chat also, so feel free to type questions in there if you have them as well. All right. So now we know, given a 3×6 matrix A, we see the null space is a subspace in R6. But how do we describe the subspace? Is it all of R6? Is it a plane in R6, a line in R6? How would you describe or show me how to generate these vectors? Okay. How do we talk about how big our subspace is in R6? Well, we can do all that by introducing these terms: basis, spanning the space, linearly independent. We talked about all these ideas at this part of the course. Okay. So basis was a set of linearly independent vectors that span a space. Two big criteria here. To be a basis, the vectors had to be linearly independent and they had to span the space. Those are the two big requirements. Okay. So spanning space means that I can build any vector in the space using the basis vectors. If I take linear combinations of the basis vectors, I can get anywhere I want in the space. Linearly dependent means there's no repetition. I don't have any extra vectors in my basis. I have the minimal number of vectors I need to span the space. Okay? It means I have a unique representation for every vector. So together, the base is the small set of vectors I can build the whole space with. So let's try some problems with basis and vector. Let's think about these three vectors: 2, 0, 0, 1, 1, 0, 3, 1, 0. Okay? 3, 1, 0. Are those vectors a basis for R3? Online crew, why don't you type your answer into the chat? Basis for R3. All right, in the chat I have a yes and I have a no. All right, are they a base for R3? Well, one, they'd have to span R3. That means I have to be able to get to any vector in R3 by taking linear combinations. Can you think of a linear combination that would bring me to this vector in R3? Is there any way I could take a linear combination of those three vectors to get to 0, 0, 1? No, I can't, right? So therefore, these three vectors do not span R3. They can't be a basis for R3. Okay, well, let's look at these vectors, though. If I looked at the span of these three vectors, I'm going to call that span V. It actually is a vector space in itself. If I were to look at the span of these three vectors, turns out all three of these vectors lie in the xy plane. 3, 1, something like this guy. Or call it the x1, x2 plane in R3. So all these vectors lie in here, and the span would be that whole plane. If I look at the span of those three vectors, if I took all the linear combinations of those three vectors, I could get anywhere in that plane that lies in R3. So far, so good. Okay. Well, these three vectors clearly span the plane. Does that mean these vectors are a basis for that vector space that is the plane? Are these vectors a basis for V? That's my next question. Are they a basis for V? Feel free to type your responses into the chat, online crew. Yes or no? Are these vectors a basis for V? All right, I have one. They are not. That is correct. They are not. And then the question will be, why not? They clearly span the space, but I have two criteria for a basis. They have to span and they have to be linearly independent. Linearly independent, okay? So these three vectors are not linearly independent. To show if they're linearly independent or not, I throw them into a matrix, do the row reduction, figure out where the pivots are. In this case, there'll be a pivot in the first column and the second column. Turns out that third vector is really just a linear combination of the other two. In fact, if I add the first two together, I get the third one, right? I don't need this vector to create that whole plane. I can create that whole plane with just the first two vectors, okay? So just the first two vectors would be linearly independent, which means a basis, I'll even give it a name, beta, the basis beta, that contains these two vectors, that is a basis for V, okay? Because I can get anywhere I want in that plane using just those two vectors, and those two vectors are linearly independent. That would be a basis for V, okay? All right. So now that I have a basis, any other vector that is in that plane, I can express uniquely by just telling you how much of each basis vector it takes to get there. So for instance, look at V. V is the vector that is 5, 1, 0. Is V, well, let's call it W because I don't want to call it V. I don't know, let's call it V because it matches my learning catalytics. Little v is in the vector space big V, right? That means I should be able to get there using a linear combination of the basis. In other words, there should be some linear combination of these basis vectors that brings me to V. Okay? And I have to look at how much of each basis vector I need. Those would be the coordinates of V. So your next learning catalytics question is to find the coordinates of V in that basis. And remember, if you have any questions along the way as we're going through this, about vocab, about anything, just shout it out. Shout it out, put it in the chat. The goal is to get your questions answered during the review session. All right, 12 students, 7 responses so far. Any the coordinates? All right, and the idea is that I could get to 5, 1, 0 if I took 2 of the first vector plus 1 of the second basis vector. That would bring me to 5, 1, 0, which means the coordinates of V in the beta basis are 2 and 1. Okay, so I guess it would be B, and apparently I copied B and made it D also, so it looks like B or D would also work. Okay, notice there's only 2 components in the coordinates for V, and that's because I only have 2 vectors in my basis. I should have 1 coordinate for each basis vector. Coordinates are how much of each basis vector I need to get to a vector. Any questions so far? Any questions so far? Check the chat real quick. Yep, B and D are the same. Yes, they are. All right, April Fools. Haha. Is there any mistake I can make today? I can just pawn it off on April Fools. Okay, I got V and I got R3. Okay, here's my question. V is a set of all vectors that lie in that plane. It's a linear combination, all the possible linear combinations, 2, 0, 0, 1, 1, 0. How many vectors are in V? Not in the basis for V, but in V. Infinitely many, absolutely, infinitely many. How many vectors are in R3? Infinitely many. Which one's bigger? V or R3? A little confusing, right? R3 feels like it should be bigger. It's all the vectors in the plane plus some more. It's bigger, right? But they both have infinitely many, which means we got to find a new way to talk about the size of a vector space. We talk about size of a vector space by using the idea dimension. The dimension is the number of vectors in its basis. Okay? The number of vectors in a basis for a space is called the dimension of the space. Okay? It's kind of like the number of different directions I can travel in. Okay? In V, I can only travel in 2 directions. That's why I was stuck on a plane. The dimension of V is 2. Okay? In R3, I can travel in 3 different directions. 3 different directions. Well, that makes sense because here's an example of a basis for R3. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? I have 3 vectors in its basis. That's why the dimension of R3 is 3. Okay? So R3 is bigger by dimension. Okay? So the dimension of a space is the number of vectors in its basis. So dimension of V is 2, means it's a 2-dimensional subspace of R3. Okay? All right. Let's tie all this stuff together, answer some questions about column space and null space. This is your next learning catalytics questions. This guy's always on the exam. I ask it a little bit different in learning catalytics, so I'm going to go like this. Really, I'm talking about the matrix that is 1, 2, 1, 2, 1, 2, 2, 3, which row reduces to that other matrix. That's how it's asked in learning catalytics. The first questions are the column space is a subspace of what? Null space is a subspace of what? Then you find the basis and the dimension. And remember, ask questions if you got them. Feel free to ask for clarification. 4 responses so far, doing pretty good. Warning, there is one kind of trick question in this one. Well, students, 5 responses so far. All right, let's take a look here. All right, so remember, if I got this guy, it's a 2 by 4. That means if I was multiplying it by some x, x would have to be a 4 by 1. The null space is a subset of the x's. So apparently the null space lives in R4. The null space of A is a subspace of R4 in this case. If I did that multiplication, the resulting B over here would have to be a 2 by 1. Column space is all the possible B's I can get. Column space is a subspace of R2. Okay? That just helps me look at my next answers for basis to kind of make sure they're checking those boxes. All right, a base for the column space. Column space is the span of the columns, right? So I know I can build the column space by taking a linear combination of those columns, but my basis also has to be linearly independent. So I want just the linearly independent columns of A. So how do I find which ones are linearly independent? I do the row reduction. It brings me over here. I see there's a pivot in column 1, a pivot in column 3. That means I grab the first and third columns of A. So a basis for the column space would be 1, 1 and 1, 2, which means the dimension of the column space would be what? 2. The dimension of the column space is 2, which means it's a two-dimensional subspace of R2. What does that mean? That means it's all of R2, right? It's a plane and a plane. So it is all of R2. So the column space is actually all of R2, which is a little bit unfortunate because E says the basis is for the column space is 1, 0, and 0, 1, which I guess is kind of true because that's also a basis for R2. And technically the column space is all of R2, right? But that is an unfortunate coincidence here, okay? In general, if you take the columns from the row reduced matrix, they will not be a basis for the column space, okay? They are in here only because the column space is all of R2, okay? So be careful. Always go back to the original matrix to find your basis vectors. Everybody happy there? Okay. That's basis for the column space. What about the null space? Well, the null space is all the solutions to AX equals 0. So if I was solving AX equals 0, I would take my original matrix and I would augment with 0 and do the row reduction. But that augmented column wouldn't change at all, so I guess this is where I would end up. All right, from there, I just write out the equations associated with each row. First row tells me x1 plus 2x2 plus x4 equals 0. Second row tells me x3 plus x4 is equal to 0. I don't have an equation that starts with x2 or x4 because x2 and x4 are free variables, absolutely. So x2 is equal to x2, x4 is equal to x4. Then I'm just going to write out my solution in parametric vector form, right? I got some x2 stuff times a vector, negative 2, 1, 0, and 0. That's x4 equals x4. Plus x4 times negative 1, 0, negative 1, 1. Okay. Are we good there? Let me know if you want me to show some in-between steps there. All right. So that means the null space, that's the null space, is any linear combination of those two vectors. Any linear combination of those two vectors. And those two vectors are linearly independent, which means these two vectors are a basis for the null space. Okay, so once I write my solution to ax equals 0 in parametric vector form, those are the basis vectors. Right? So the basis for the null space would be negative 2, 1, 0, 0, and negative 1, 0, negative 1, 1. Which means the dimension of the null space is what? 2. The null space is a two-dimensional subspace of R4. And lastly, I'm pretty happy with those dimensions because the null space, the dimension of the null space, will have one basis vector for each free variable. So the dimension of the null space is going to match the number of columns without pivots, because those are the ones that have the free variables. The dimension of the column space is actually going to be the same number as the number of columns with pivots, since those identify the linearly independent columns. Which means if I take the dimension of the null space plus the dimension of the column space, I should get what? If I take the number of columns with pivots plus the number of columns without pivots, number of columns, right? The number of columns of the matrix. So in this case, there's 4 columns. Dimension of the column space is 2. Dimension of the null space is 2. They add up to 4. That's a little check, mental check for myself. Okay. All right. Any questions so far? Everybody doing good in the online group? No questions at all? Tracking okay? Okay. All right. All right. So that finishes up spaces, and we got to determinants. So you had to do all kinds of determinant calculations this part of the course. So you should know to calculate the determinant of a 2 by 2, we have a little formula, which is this product, 1 times 7, minus that product, 2 times 3, determinant value of 1. That was the nice one for 2 by 2s. It was harder for 3 by 3s and bigger. We had to expand along rows and columns. So we had our process for that. So here I have a 4 by 4. Your next question in learning catalytics is to find the determinant of that 4 by 4. So I will deliver that one to you. Find the determinant of that 4 by 4. Expand along any row or column you choose. I know I would expand along a row or a column with a lot of zeros. That tends to make things faster. One response, 100% correct. All right. Well, students, 4 responses so far. All Right, 12 students, so it's 6 responses so far, tracking about 50% correct. All right, I'm going to start working on my problem here. Remember, I can expand along any row or column. I'm going to expand along the second row because there's a bunch of zeros. And then for every spot, I have a sign, I have a coefficient, and I have a determinant. So starting in the top left, that'll be positive, minus, positive, minus, positive. Next, we have a sign associated with the position. So as I expand along that second row, I'm going to get negative 0 times something. I don't care because it's 0 times something. Plus 0 times something, don't care. Minus 1 times a subdeterminant, and then plus 0 times something. And the subdeterminant I get here is the matrix I have left when I eliminate the row and column of that one. So it looks like I'm left with 2, 1, 3, 1, 3, 2, 0, 0, 4. So now I have to do a 3 by 3 determinant. Once again, I see a row with almost all zeros, so I'm going to expand across the bottom row. I got plus, minus, plus, minus, plus. So it looks like I'll have plus 0 times something, minus 0 times something, plus 4 times something. So I will have my minus 1. I will have plus 4 times the subdeterminant when I eliminate the row and column of 4. So I have 2, 1, 1, 3. So this is negative 4 times 6 minus 1. Negative 4 times 5 is negative 20. That should be my value. Any questions about calculating that determinant? That's one of those mechanical processes you just got to get down, right? Just got to do a bunch of determinant problems. Any questions there? Expanding down rows and columns. All right. Other things we learned about for determinants were a bunch of properties. I had a bunch of core properties with determinants. One example would be if the determinant of A is negative 2 and the determinant of B is equal to 6, what's the determinant of A times B? Online crew, want to hit the chat room, hit the chat box there? Or turn your mic on, either way. Determinant of A is negative 2, determinant of B is 6, determinant of A, B is... All right, negative 12, absolutely. Because the determinant of a product is the product of the determinants. That's our product. So now we can just write negative 12. Okay, makes easy calculation. What about the determinant of A transpose? Well, what is A transpose? When we transpose a matrix, we're just switching the rows and columns. And if I can expand down any row or column to do a determinant, I guess I don't care if rows are columns and columns are rows. So the property here is the determinant of A transpose is just the same thing as the determinant of A. Taking a transpose doesn't change the determinant. Another property I forgot to write down here was the determinant of A inverse. All right, we have a property there that you saw in your written homework. Determinant of A inverse is 1 over the determinant of A. Hopefully you proved that on your homework. Okay. What about the determinant of a triangular matrix? Let's say I want to find the determinant of this guy. 1, 2, 3, 4, 0, 2, 4, 9er, 0, 0, 1, 14, 0, 0, 0, negative 1. What's the determinant of that matrix? Special way we can calculate the determinant of a triangular matrix. That's right, diagonal matrices, absolutely. So we can just take the product of the diagonal elements. 1 times 2 times 1 times negative 1, negative 2. So that's a nice shortcut. If you have a triangular matrix, you can just take the product of the diagonal entries. And then we have one big theorem for determinants, that a matrix A is invertible if and only if the determinant of A is... is what? Not equal to 0, right? Because one of our formulas for the inverse of a 2 by 2 is 1 over the determinant times some stuff, right? So if the determinant is 0, we'd be dividing by 0, and only Chuck Norris can do that, right? All right, so if the determinant is 0, the matrix is not invertible. And why do we really want that? Well, to investigate AX equals 0 is one way we use this. Because the idea is if that A was invertible, the only solution would be X equals 0. And there are times when I'm looking for non-zero solutions for that, non-trivial solutions. So if we have the determinant of A is equal to 0, that would imply that A is not invertible, which would imply that there will be non-zero solutions to AX equals 0. Okay, so if the determinant is equal to 0, there will be non-zero solutions to AX equals 0. Now, why is that important? Because we use that idea when we calculated eigenvalues and eigenvectors, which is the last big topic of this part of the course. All right, so eigenvalues, eigenvectors. We had a big idea here. AX equals lambda x. That was our concept for what eigenvalues, eigenvectors were. It's a special vector and scalar related to our matrix, where if you take the matrix times the vector, all you're really doing is scaling it. It's kind of a special transformation. That equation was great. Didn't really help us find out what lambda and x were, though. So what we did was we subtracted lambda x to the other side, and then we factored out our x to get a nice homogeneous equation. So really, I just want to solve that guy. Problem is, that's one equation, and I have two unknowns, lambda and x. But I am looking for non-zero solutions. There are my eigenvectors. I'm looking for non-zero solutions to that homogeneous equation. That can only happen if the determinant of that matrix is equal to 0. So that's exactly what we do. Given a matrix A, to find the eigenvalues and eigenvectors, we first solve the determinant equals 0 to figure out the lambdas. Those will be the lambdas that will give us non-zero solutions for x. Set the determinant equal to 0, find the eigenvalues. Next, for each eigenvalue we found, we solve the homogeneous matrix equation. And that's a reminder of our steps for eigenvalues and eigenvectors. So let's get some practice in finding eigenvalues and eigenvectors. That guy, and go ahead. And that is your next learning catalytics question. Twelve students, 2 responses so far. Calculating the eigenvalues and eigenvectors. All right, quick check-in. Those are my eigenvalues. I calculated a minus lambda I, which basically subtracts lambda on the diagonals. And then I calculated my 2 by 2 determinant, set it equal to 0, got my eigenvalues. Any questions about the eigenvalues? Any questions about the eigenvalues? 12 students, 6 responses so far. All right, now for each eigenvalue, we have to find the associated eigenvector. All right, remember, all we have to do is solve a minus lambda I times x equals 0, the homogeneous matrix equation. So I say if lambda equals -1, chose an eigenvalue. Right? So that means a minus lambda I is subtracting -1 on the diagonal. That will leave me with 1 minus -1, 2, 1, and minus -1. Okay? And so I'm basically trying to solve this homogeneous matrix equation. To do that, I just need to row reduce, augment and row reduce. And this guy row reduces to this. I can see those two rows are just multiples of each other. Divide the first row by 2, take row 2 minus row 1. That's the guy I get. Okay. I write out the equation for the first row. I get x1 plus x2 equals 0. I know that x2 is a free variable. Solve the first one for x1. x2 is free. Looks like my solutions in parametric vector form are x2 times -1, 1. There's my eigenvector. So I could look at the eigenpair that when lambda equals -1, the eigenvector would be -1, 1. And that would be option C. But remember, any multiple of an eigenvector is also an eigenvector. So I could have used -2, 2, -4, 4. All of those would be valid eigenvectors because any multiple of an eigenvector is also an eigenvector. In fact, answer B is really just -1 times this eigenvector, so that would also be a valid eigenpair. Any multiple of an eigenvector is also an eigenvector. All right, so now I got to do the same thing with my other eigenvalue. If lambda is equal to 2, I get -1, 2, and 1, -2. Basically subtracting 2 on the diagonals of A. Solving the homogeneous equation, so I augment with 0, do my row reduction. This guy turns into 1, -2, 0. Once again, those rows are multiples of each other, but I know that's always going to happen for a 2 by 2 because I have chosen lambda, so there will be non-zero solutions. I've chosen lambda, so there has to be a free variable because I can't have a pivot in that second row. Okay. Now I write out that equation. x1 is equal to 2x2. x2 is free. My solution in parametric vector form is that guy. That should be my solution. Lambda equals 2 gives me the associated eigenvector of 2, 1, which is actually not an option there. Okay. Any multiple of an eigenvector is also an eigenvector, but none of those options are straight multiples of 2, 1. Any questions so far? Any questions? All right, what do we use our eigenvalues, eigenvectors for? Well, one thing we use them for is to diagonalize a matrix. So I can rewrite A as P times D times P inverse, where the matrix P has columns that are the eigenvectors. So I just take my eigenvectors, write them in for the columns of P. D is a special matrix, it's diagonal, where the diagonal entries are the eigenvalues. And once I know what P is, I can calculate P inverse. In this case, it'd be 1 over -1 minus 2. And I switch the values on the strong diagonal, change the signs on the off diagonal. I got my little formula for the inverse. Okay, so once you know the eigenvalues, eigenvectors, you can just kind of throw them into the matrix P, throw them in to get the matrix D. Any questions there? And that's really handy if I want to take matrix powers. Okay. So in general, taking the power of a matrix is hard because I can't just raise the individual values to the power. Like in this case, my A was this. A to the 10th is not 1 to the 10th, 2 to the 10th, 1 to the 10th, 0 to the 10th. That is not how we take matrix powers. We have to take A times A times A times A 10 times. But because we can diagonalize this, we know that it's really just P times D raised to the 10th times P inverse. And that's handy because if I have a diagonal matrix and I raise it to the 10th power, then I can really just take each of the pieces to the 10th power. So this would be an expression for A to the 10th. The nice thing is now I don't have to multiply 3 matrices instead of 10 matrices. Okay? So that would be my expression for A to the 10th. Any questions there? Talkative group tonight. I know, we're all still stunned from the Duke loss, aren't we? Is that what it is? The tournament got people down? Some busted brackets out there? All right. Could be. Michigan State looking good. All right. All right. Any questions? Any questions so far? Okay. So that's eigenvalues, eigenvectors, and diagonalization, but it's kind of the easy case here, right? So that's a reminder what that is. Matrix P, matrix D. But the question is, when can we diagonalize that? And to answer that, we'll look at the different possible outcomes for eigenvalues. We calculated our eigenvalues. We took that determinant and set it equal to 0, but that determinant just always gave us an nth degree polynomial. So if I had an n by n matrix, I would get an nth degree polynomial. Every nth degree polynomial has n roots. Okay? If I get distinct roots, if I get lambda equals 1, 2, and 3, every time I plug those back in to find an eigenvector, I'll get an eigenvector. I will have 3 eigenvectors. I can form my matrix P. It will be square. Everything will be right with the world. I can diagonalize. Yay! Okay. Now, if I have repeated eigenvalues, lambda equals 2 and then 1 and 1, ooh, well now I'm not sure. If I plug in lambda equals 2, I will get an eigenvector. If I plug in lambda equals 1, sometimes I'll get an eigenvector that looks like this. I'll say, oh, I plugged in lambda equals 1, but I have 2 eigenvectors. Perfect. Now altogether I'll have 3 eigenvectors, and I can form my matrix P, and I can diagonalize. So sometimes everything will be okay. Sometimes when I plug in lambda equals 1, I will only get 1 eigenvector, which means my total will only have 2 eigenvectors, which means when I plug those in for my matrix P, it will not be a square matrix. I will not be able to find the inverse. I will not be able to diagonalize. So it just depends if you get enough eigenvectors. Doesn't depend on the eigenvalues. Depends on if you get enough eigenvectors. Any questions? So I got one in the chat. Let me swing over there. Oh, no problem. Some people might have to leave here. I'm right at the end, about 9 o'clock. I have 2 more examples to go through, complex and repeated root case. But if you have to go, I totally get it. So no problem. Any questions so far about that case? So repeated roots. Sometimes I'll be able to diagonalize, sometimes I won't. And the last case was the complex case. Right? We plug them in, we get complex eigenvalues. And instead of being able to diagonalize, we can instead have a different factorization. We can't find P times D times P inverse, but we can find P times C times P inverse, where C is a rotation matrix instead of a diagonal matrix. Okay? And we have a formula of that. If I find lambda to be this, A minus BI, then my matrix C is that guy. Right? So they kind of come in pairs. So when we use lambda equals A minus BI, that's our formula for C. So now I got one example of each, and that should finish off the review session. So find the eigenvalues and eigenvectors and decompose if possible. Okay. So here I got my first one. 1, 0, 1, 0, 2, 2, 0, 0, 2. Step number 1, calculate A minus lambda I, set it equal to 0. So I subtract lambda on the diagonals. Actually, you know what? I don't even do that. I don't do that. Why not? Instead, I will just write down what the eigenvalues are using my psychic ability. No. We can look at this matrix and right away know what the eigenvalues are. There we go. Jake mentioned it. It's a triangular matrix. So right away, I know that the eigenvalues are 1, 2, and 2. Because it's triangular, I can write that down. Then to find my eigenvectors, I need to solve A minus lambda I times x equals 0. So I say if lambda equals 2, for instance, I'll use the repeated value first. Well, then A minus 2I would be subtracting 2 on the diagonals. I'll get negative 1, 0, 1, 0, 0, 2, 0, 0, 0. Augmented with my zeros. I'll do my row reduction. I will multiply the first one by negative 1, multiply the second one by 1/2. Then I will take row 1 plus row 2. When everything is said and done, I will get this guy. I'll write out the associated equations. x1 equals 0, x3 equals 0, x2 is my free variable. Looks like my solutions look like 0, 1, 0. I had lambda repeated twice, but I only got one eigenvector. That tells me in this case, I cannot diagonalize my matrix. Not because the eigenvalues are repeated, but because I didn't get enough eigenvectors. Sometimes I will, sometimes I won't. Any questions there? And then lastly, the big complex case here. All right, I start by A minus lambda I, which means I subtract lambda on the diagonals, calculate the determinant, 1 minus lambda, 3 minus lambda, minus negative 10, which is plus 10. And then I distribute. I will get 3 minus lambda, minus 3 lambda, plus lambda squared, plus 10. Lambda squared, minus 4 lambda, plus 13. When is that equal to 0? I try to factor, I try to think of all the factors of 13. They are 1 and 13. Not seeing how to factor this guy. What do? Quadratic formula. All right, so I got lambda is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. In this case, that's 4 plus or minus 16 minus 4 times 13, which is 52, all over 2. 4 plus or minus the square root of what? 16 minus 52 is negative 36. And then the square root of negative 36 is 6i. Divide everything by 2, I get 2 plus or minus 3i. So those are my eigenvalues. Lambda is equal to 2 plus or minus 3i. Okay, so I found the eigenvalues. Now I got to find the eigenvectors. All I got to do is solve, just like before, a minus lambda I times x equals 0, the homogeneous equation. I'm going to choose lambda equals 2 minus 3i. I'm choosing lambda minus 2 minus 3i. You choose the negative one because that's how our formula for C was built. Okay, using the negative eigenvalue. Let's choose that guy. If lambda is equal to 2 minus 3i, then I plug it back into a minus lambda I, and I will get 1 minus the quantity 2 minus 3i. I always write the quantity, that way I don't forget to distribute my negative sign. 3 minus the quantity 2 minus 3i, augmented with 0. Simplify a little bit, I get negative 1 plus 3i. And I get negative 2 and 1 plus 3i. And now what? Now, because I have a 2 by 2, and I know there have to be non-zero solutions, I know that these two rows are just multiples of each other. It's hard to see, but they are. They are multiples of each other. Right? Turns out I have to multiply the top row by like negative 1 minus 3i to turn it into a real number. But if I did that, I would find out that these guys really are multiples of each other. They have to be. I have chosen lambda to make sure these guys are multiples of each other. So because that, I know that if I wanted, I could simplify this through row operations to this. Or I could simplify it to this. If I swap the rows, I could do that. I could do either of those. Okay? I am choosing to use the second row. I'm choosing to use this one. Either is fine, but the second one is easier to solve. So I would encourage you to choose the second row. When I do that, I write out my solutions. Negative 2x1 plus 1 plus 3i times x2 is equal to 0. And x2 is a free variable. Okay. I take the first equation, I solve it for x1, subtract that to the other side, divide it by negative 2. I'm going to get positive 1/2 plus 3/2 I times x2, and x2 is free. I'd write my solution in parametric vector form. It's x2 times 1/2 plus 3/2 I and 1. And that would be a perfectly good eigenvector. It's not the eigenvector I'm going to choose, but it's a perfectly good eigenvector. But any multiple of an eigenvector is also an eigenvector, and I hate fractions. So I'm going to just choose to multiply my eigenvector by 2. And then I'll get 1 plus 3i and 2. Okay? And I do that for good reason. In your next class, in differential equations class, you have to use these eigenvalues and eigenvectors to form solutions to big differential equations. And then you have to do algebra with them, some other junk with them. And I want to work with 1 plus 3i, not 1/2 plus 3/2 I. Okay? So I do want to just clear those fractions. You don't have to, but I recommend you doing it. Okay? All right, so now I have my first eigenpair. Do I have to do the same thing with lambda equals 2 plus 3i? Turns out I don't. The eigenvalues come in conjugate pairs, and so would the eigenvectors. If I plug that in, I would get this, because they always come in conjugate pairs, so I don't have to do that. And lastly, all we have to do is write out the decomposition. A is equal to P times C times P inverse. Okay. For my matrix P, I look at my eigenvector, and the first column are the real parts, and the second column is the imaginary parts. And both components have a real and imaginary part. I can think of 2 as really being 2 plus 0i. All right, so now for my first column, I get the real parts of my eigenvector. I have 1 plus 3i in the top component. The real part is 1. The real part of the second component is 2. The second column is the imaginary parts of my eigenvector. Those are the coefficients to the I. It does not include the I. So 1 plus 3i, the imaginary part is 3. 1 plus 0i, the imaginary part is 0. That's how I form my matrix P. And then my matrix C, That's the A minus B, BA. And since I'm using lambda equals this guy, it says if lambda equals A minus BI, that tells me that A is 2 and B is 3. And then my formula is A minus B, B, A. And since I know what P is, I could always calculate P inverse. So that's how I form my matrix P and my matrix C when I have complex eigenvalues and eigenvectors. All right, a lot of stuff there. Any questions?
In the composition for complex roots, the formula for C is, what was it for C again? Like the general.
So it's paired. So if lambda is equal to A minus BI, then C is A minus B, B, and A. It's a rotation matrix. So our general rotation matrix is like cosine theta, negative sine theta, cosine theta. So that the fact that they have the same values on the strong diagonal and the off diagonal just changes by a sign, that's like the nature of a rotation matrix. Other questions? Any questions? Dropping like flies in the online session, down to 6 people. Any last questions? All right, that concludes the review session. Keep prepping, keep working through that practice exam too. If you have any questions, feel free to email me, right? Or call me or text me or whatever it takes. Exam is on Wednesday. All right, have a good night.